So, this is revision day 2, design of lined canals. Yesterday we read all about design of unlined canals, and so in lined canals, while designing, we consider the shape of cross section to have rounded corners, not sharp corners, and the shape can be trapezoidal or triangular with rounded corners, of course. And regarding freeboard, there are certain ranges. That is, if the canal discharge is greater than 10 meter cube per second, then freeboard should be 0.75 meter. If it's between 3 to 10, then it's 0.6 meter. If it's 1 to 3, then 0.5 meter. If it's less than 1 meter, cube per second, then the freeboard should be 0.3 meter. And if it's less than 1 meter cube per second and it is a water course, then freeboard should be half of 0.3, that is 0.15 meter. Now, there is a limit on the non-scouring velocities of channels having that are made of different materials. That is, if the channel is stone pitched lining, then the non-scouring velocity is 1.5 meter per second. If the channel is made up of cement concrete, then it's 2.7 meters per second. And if the channel is lined with burnt clay tile or it's lined with bricks, then it is 1.8 meter per second. And the Manning's formula is used to compute velocities of these channels. If it's a trapezoidal section with rounded corners, then area is given by BD plus D square multiplied by theta plus cot theta, and wetted perimeter is given by B plus 2D into theta plus cot theta. And if we need to find out area and perimeter of triangular section with rounded corners, then simply put B is equal to 0 in formulas for trapezoidal section. Tractive stress based approach. Coming to tractive stress based approach, we have many theories, but for Indian conditions, Shields theory is the most appropriate. And there are two assumptions in this, that is, soil is non-cohesive and flow is steady and uniform. In Shields theory, in short, we just compare the two stresses, that is, the actual stress and critical shear stress. For trapezoidal section, for trapezoidal channel, if for non-scouring of bed, the tau actual on bed should be less than or equal to tau critical for bed. And similarly, for non-scouring of side slopes, the tau actual for side slope should be less than or equal to tau critical for side slopes. The stress distribution on the trapezoidal channel for the bed as well as side slope is as given in the figure. For bed, it's equal to gamma W RS, and for side slope it's 0.75 gamma W RS. And in case of wide rectangular channel, the side slopes exert negligible shear resistance, and whereas the bed shear stress, actual shear stress on bed is given as the same for trapezoidal section, that is gamma W RS. Once we are done finding the actual stress, now we need to compare it with the Shields critical stress. Shields critical stress there is, in the first case, for bed of trapezoidal or wide rectangular channel, tau critical for bed is equal to 0.056 gamma WD multiplied by GS minus 1. And for side slopes of trapezoidal channel, it is tau critical for side slope is equal to 0.056 gamma W into D multiplied by GS minus 1 multiplied by whole under root 1 minus sine square theta by sine square phi, where theta is the angle of side slope from horizontal and phi is the angle of repose of soil. Now, while comparing for the stability of bed, tau actual of bed should be less than tau critical for bed, and on simplifying the expression we get D should be greater than or equal to 11 RS, where D is dia of silt particles and S is the bed slope. Now, Shield's expression is valid only when dia of silt particles is greater than 6 mm. And for a rigid boundary channel, roughness coefficient, or which is also called Manning's N, is given by Stickler's formula. The formula is N is equal to, that is Manning's N is equal to D raised to the power 1 by 6 divided by 24, where D is in where D is in meters. Okay, and we also have another formula similar to Shield's that gives similar result to Shield, that is Mittal and Swami. We can use this formula for all D's, but it is more suitable for D less than 6 mm. So, tau critical for bed in SI unit is equal to 0.155 plus 0.409 D square divided by under root 1 plus 0.177 D square, where D is in mm. In all the previous formulas, D, everything was in SI unit, but here in Swami and Mittal's formula, the D is in mm. Okay, that's it.